we will talk about time and clocks in distributed systems. So in this lecture, we are going to go back and use a physical notion of time and a physical clock and see what can we do with this notion in distributed algorithms. So this lecture is, or these slides are done by Niklas Ekström, and I'm going to present it. So here's an outline of what we are going to do. We are going to start by a motivation for using clocks. And in particular, we are going to look into two algorithms. One is time-based leader leases. So if you remember the replicated state machine and sequence Paxos, every group of replica will have a leader, and with time-based leader leases, we will make a leader guaranteed to acquire this role for a period of time. That is called time lease. The second algorithm is an algorithm for shared memory. If you remember the read-write register algorithms, we will see if we have some loose notion of clock synchronization, which we will describe later. So the issue is, can we make a better algorithm? Well, by better means more efficient algorithms. So why would we consider algorithm using clocks? First of all, we consider algorithm using clocks because, first of all, it is possible in the real world to be able to use clocks, even if the clocks are not synchronized. And by making a little bit more stronger assumption about the system, we can get a better efficiency and performance. So this little bit stronger system model will add some form of limited assumption about synchrony. These assumptions are actually achievable in real systems. Still, this is weak enough. So even in this slightly stronger model, we will not be able to solve problems that are harder than what we have can be solved in asynchronous model. Still, the FLP consensus impossibility result still holds, and in fact we cannot get rid of the unpredictability in asynchronous system of the time it takes for messages to traverse between nodes. Okay. So let us look to time-based leader leases. Here is an outline of the leader leases algorithm. Problem. We will do this by looking to the optimization opportunity by using, in fact, local clocks, and we are going to show then a proposed algorithm, and we are going to argue why this algorithm is correct. So here's some background. So we would like to implement a key value store, or in fact a shared memory, using replicated state machines. And we will assume that this replicated state machine will support the following commands. What are the commands? You can read an item given the key. You can update or write an item with given key k with a new value v, and you can implement an operation that in the class of read modify writes called cas, compare and swap, And here is the specification of compare and swap in case you haven't seen it before. So compare and swap takes a key, an expected old value, the value is supposed to be there, and a new value. And the compare and swap writes this new value only if the old value is the expected value and returns the old value. If the old value is not, the old value that is stored in this item is not the expected value, then it does not update that item, but it always returns the old value. Okay. Very good. So in fact, this operation, which compare and swap, requires a stronger model than just the shared read-write register that we described in some previous lecture. So the shared memory model that we described is too weak, and in fact, so it needs consensus, or basically it needs replicated state machine to implement it. So we assume that the service runs with 3 replicas, which is P1, P2, and P3, and each act as a proposer, acceptor, and learner. Okay. If you remember replicated replicas in multi-paxos, so this is what we are talking about. Here we have the 3 replicas, P1, P2, and P3. And normally, we have seen from sequence paxos, multi-paxos, is that one of these replicas will act as a leader and will be a proposer, and all of them will act as acceptors and learners. Okay. And in fact, when this replicated state machine gets command, it will order the commands. Okay. So Paxos guarantees that all replicas execute the command in the same order, as we know. So here is an example of sequence of commands. So if you have the old state empty state, nothing there, and then you do the command write x equal 1, terminates with OK, and now we have x equal 1. If you have x equal 1 and you write y equal 0, then you add, now our state has x equal 1, y equal 0, and this is for all the replicas in the replicated state machine, and so on, one command as another, as after each other. So for example, here is an interesting command, which x equal 1 and y equal 0, and we do a compare and swap on y, and if the old value of y is 0, we atomically replace it by 1, and we return the old value, and that's what happened here, and we replaced now y is changed from y equal 0 to y equal 1, and so on. So this is how a replicated state machine work, and that this sequence of command, this evolution of state, happens on all machines in the same order. Okay. Now let us see how these things execute. Say we have this replicated state machine consisting of these 3 nodes, P1 to P3, but we can have any number of clients that really uses the replicated state machine as a service. Okay. And let's assume that the network is stable and P1 is a leader and has started a higher round. So P1 is a leader, it got the promises from all the acceptors, and it is running, and it is the one that is accepting commands and proposing commands. I mean, it's the one that accepts commands from the clients and then propose the commands. Okay. So here is our system. We have P1 to P3, and we have the clients that are shown in blue here. Okay, so let us see how a command executes in this system, and then after that let us see if there is an opportunity to improve the execution. So we assume here client 4, P4, wants to execute a command, and it sends a request of this command to P1. So this is what we have seen here. So P4 in 1 sends request to P1. Okay, that's what we have seen. Fine. So what happens at P1? P1 is a leader, so P1 can, what does it do? B1, it is a leader, so we have first, we said P4 send request to P1, and P1 is a leader. P1 will send an accept command here to the other nodes and to itself. So this is P1 to P3. Fine. So this is the proposed commands, and when the replicas accept, of course, the command and respond with an accept ACK message. Now he has a majority of an accept ACK message, for example, from himself and P2, and then P1, when it gets an accept message from a majority, the command order is chosen. This is really the command, and P1 executes and sends a decide message. So executing, sending a decide message this is really where the command is executed. It will be executed locally, and at the same time the results of that will be sent to the client. That's P4. So P1 executes the command using the state machine, the state of the state machine, of course, and sends the response with result of the operation to P4. So let us see now how many steps happen here. So P4, in the first communication steps, first communication step, it talks with P1. P1 talks with a set of nodes, including, say, P1 and P2. This is, he gets an acknowledgement. So we get P1 again. We get an acknowledgement. This is step number 3. 3 steps. Now from a majority, so I will say it's from a majority, and then it itself executes the command locally and send a message to P4 here. This is step number 4. So we have 4 communication steps to execute the command. So this is the normal step when you are executing with a replicated state machine. If the client is not one of the nodes in the replicated state machine, when the client issues the command, until it gets a response, it takes 4 communication steps. So this is in general. But in fact, what we can do is that we can, in the case where the command is a read command, we are able to shorten this chain of sequence into 2 communication steps. Let us see if that is possible. That's what we are going to do here. So here is an opportunity for optimization, which we call faster reads. So assume now the operation requested by P4 is a read. So the command is read X. Okay, that's what we see here. So let's see what happens. Here is what we want to do. So we want to send the command from P4 to P1. And since P1 stores the entire state, so P1 should be able to read the state variable x and respond immediately. And that means that to complete this computation, we will only require 2 communication steps. Here is the first step, communication with P1. P1 has the state, so it can respond to the read, and it responds back to P4. So the question is this is valid execution even when we have a strong linearizable model? Say it in another way. Can actually P1 respond immediately? So let us look to this. In fact, this is not correct, and let us see what is going to happen and how things can go wrong. Okay. So here is a scenario. We start from that scenario which says a network first split happens, and that partitions P1 away from P2 and P3. So let us look like this. Okay, so that is fine. And then P2 is elected as a leader here. But because of the network partition, P1 never hears about this, and P1 thinks he's still a leader. Nothing has changed. So now let's assume that this client, P9, sends a write command or a write request to P2. So P2 communicates with P3, which is fine, and he gets a majority of acceptors. So he communicates with P3, gets the accept X, and he gets a decision, and then he sends the results to P9 through this message. Okay. Now, after that, P1 gets the read from P4, and it responds. That's it. So because P1 is unaware of the split and the write operation, of course, he doesn't know about it, and the response to P4 will happen with an old value. It is, so he will be reading the value of x after P9 has written the value of x, but he is going to return an old value. This is not allowed if you have linearizable strong consistency. In fact, this operation is allowed if you have, say, sequential consistency, because sequential consistency order or the writes and the read can happen anywhere. But in this case, if we want linearizable strong consistency, so linearizability is violated. Okay, so here is a problem summarized. The reason P1 cannot respond with its current state is because some other replicas may have assumed leadership and modified the state without P1 knowing it. Okay. So the question is, can we avoid this? I mean, one possibility is to let force P2 to communicate with P1 before it becomes a leader, but this is not possible because this will allow the system to be unavailable once there is a split or a partition in the system. So this is not really a good solution, because even that is one thing. The second thing is P2 even doesn't know if P1 is still alive or not, and we just require a majority to be alive. So this is not a solution. Okay. So the solution to this problem is to try to guarantee that P1 will be a leader for a period of time. And during this period, no other node is allowed to assume the role of leadership or leader. And that's what we are going to discuss in the next unit. Thank you.